Suppose you were in charge of the marketing strategy for some company, and you had to devise an online advertising scheme to reach as many people as possible. Your first option is to sponsor YouTube creators, and you found that there are 30 medium-sized creators whose target audience matches your product's intended demographic. To sponsor one creator, you would be paying $1,000, reaching about 25,000 people. The second option is running advertising campaigns on social media like Instagram or Facebook. One campaign costs $500 and reaches 12,000 people. However, you are told to run at least 20 of these campaigns to keep up the company's presence in the space. Your marketing capital is $50,000, which you must not exceed. How do you distribute the money between the two advertising vessels to maximize the number of people reached? The setup of this problem follows a format that is very common in business and industry, but before we investigate further, let us first translate it mathematically. If we denote by X the number of YouTube creators we will sponsor, and by Y the number of social media advertising campaigns, our goal is to maximize this quantity representing the number of people reached, subject to certain conditions. First, we must not exceed our total budget. And second, there are only 30 YouTube creators we can sponsor, and third, we must run at least 20 social media campaigns. Of course, we can't sponsor a negative amount of people or run a negative number of ad campaigns, so we also specify that X and Y have to be non-negative. The problem you are looking at is formally known as a linear program, which, despite the name, has nothing inherently to do with a computer program, as in writing code. You can write a computer program to solve a linear program, more on that in the future, but a linear program is just an optimization problem with certain characteristics. So the goal is to maximize or minimize a quantity formerly known as the objective function, given as a linear function of two or more variables. More on linearity in a minute. We are also given certain conditions or constraints on those variables. These constraints must either be loose inequalities in either direction, as we have here, or they can be equalities, which we do not have in our example. Importantly, strict inequalities are not allowed in a linear program. Note that the left-hand side of these constraints must also be a linear function of our variables. Finally, the non-negativity condition is present in all linear programs, for technical considerations that it is too early to discuss. Let us now clarify what we mean by a linear objective function. For those familiar with linear algebra, it just means that the objective function is given as a dot product between a constant vector c called the cost vector and the variable vector x, which contains all of our variables, in this case x and y. And for those unfamiliar with linear algebra, it just means that the function is given as a sum of terms, each consisting of a constant multiplied by one of the variables. So no powers higher than 1 or other functions of the variables, and no combining multiple variables into one term in the sum. The same also applies when we say linear constraints, except that in this case we also have a right-hand side term which is some constant. Now, while we try to optimize our fictional YouTube sponsorships on one end, it seems that Brilliant's optimal strategy has included sponsoring this channel, because this video is brought to you by Brilliant. Brilliant is a multi-platform learning app that focuses on learning by doing. Its lessons are highly interactive and are designed to guide you towards analyzing problems, identifying patterns, and finding solutions on your own, making you a better thinker and a competent problem solver. You won't simply be memorizing concepts to pass your courses. You'll be equipped with the reasoning skills to actually do something with that knowledge and conquer real-world problems. Brilliant offers many courses in mathematics, computer science, data analysis, and artificial intelligence, all crafted by award-winning experts from Stanford, MIT, Microsoft, Google, and more. We like Brilliant because its bite-sized lessons make learning possible even if you're pressed for time, and its streak system helps you keep track of your goals, making progress every day and build your habit of learning. They've got something for everyone, no matter if you're a beginner or an expert, so don't miss out on the opportunity. To try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/mathverseanimated or scan the QR code on screen, or you can click on the link in the description. You'll also get 20% off an annual premium subscription. Thanks once again to Brilliant for sponsoring this video. Going back to the problem, your first instinct inherited from real analysis when met with a problem involving a maximum or a minimum might be to differentiate the objective function and examine its critical points. But as we will see, the challenge with these kinds of problems isn't actually the function itself, which has a very simple linear form and isn't bounded on all of R2 anyway. It is actually the constraints which create the most difficulty, as they can make the space we need to search for the optimal solution much more complex and less regular than what we're used to dealing with in regular two-variable calculus. So let's try to visually see this space. We will use the two axes of the plane to represent our variables x and y. To visualize the parts of the plane which satisfy one of our constraints, we can transform inequality into equality, which gives us the equation of a line that we can draw. This line divides the plane into two regions, one of which is the region that satisfies the inequality constraint. We can determine which one it is by checking whether the origin, for example, or any other point satisfies the inequality or not. In this case, it does, so the half-plane containing the origin is the one we want. We can continue doing this with the rest of the constraints, where we always take the intersection of the half-plane the new constraint gives us with the region that resulted from the previous constraints. After we have used all of the constraints to slice away regions of the plane, what we are left with is the space we need to search for the maximum solution. It is formally known as the feasible region, and its points are called feasible points, meaning they satisfy all constraints. If we bring back the expression for the objective function z and switch in the unit to thousandths for convenience, we can see that each point on the feasible region corresponds to some value of the objective function. Now consider the cost vector c. Let us draw it on the plane along with the line perpendicular to it which passes through the blue point. Note that the lines may not look perpendicular in this illustration, but that's just because the units on the x and the y axis are not equal. Notice that as we move along the perpendicular line, the value of the objective function stays the same. Why is that? Well, let's denote our current position by p, and a vector representing a movement along the perpendicular line as u. Bringing back the dot product form of the objective function, we can distribute the product across the two terms, and since u is perpendicular to c, their dot product is 0, meaning we can keep the same value for the objective function that we had at p. Then for any movement vector u, we can decompose it into two components, one parallel to the cost vector and one perpendicular to it. Since the component along the perpendicular direction does not contribute to the value of the objective function, the value at the new position takes the following form. Being parallel to c is equivalent to being some constant multiple alpha of c. So after some simplifications, we find that the value of the objective function changes by alpha multiplied by a positive constant. In fact, this means that moving in the same direction as the cost vector increases the value of the objective function, and moving in the opposite direction decreases it. Equipped with this knowledge, it becomes simple to find the maximum we are looking for. Starting at the point 0,20, the objective function takes a certain value. Then as we move the red line, which is perpendicular to the cost vector, although again doesn't look like it, along the direction of the green cost vector, the value of the objective function increases, where the points of the red line all have the same objective function value as established earlier. This continues until the line eventually completely leaves the feasible region. Then the optimal solution or solutions are the last set of points of the feasible region that the line intersects before leaving the feasible region. In this case, it is a singular point 3040 with a value of 1230, which is the largest possible in the feasible region. That works, but what if the company decides to also run television ads? We need to add a third variable, say t, that would also introduce its own constraints. The feasible region becomes three-dimensional, and the movement vectors which leave the objective function constant now form a plane rather than a line. We would be sliding this plane parallel to the new cost vector and finding the last set of points it intersects before leaving the feasible region. Now what if we add a fourth variable for billboard ads? Not only is the situation getting increasingly complex, it also becomes impossible to visualize as the number of variables increases beyond 3. You might think that we can apply the same idea just without being able to see the feasible region, but this process of finding the last set of points the space intersects before leaving the feasible region is just a reformulation of the linear programming problem itself. We were just relying on our ability as three-dimensional beings to visually scan the portion of the feasible set all at the same time and determine where the optimal solution must be. And sure, there are some tricks and clever manipulations you can throw at the more complex problems, but the question is, what do you do when you run out of tricks? Away from our oversimplified example, linear programs occur all over business, finance, healthcare, engineering, and more, with problems having hundreds or even thousands of variables and constraints. We need to be able to find solutions to these problems, and we need to be able to do it quickly and efficiently. While this first part serves as a gentle introduction to linear programming, future parts will cover what most would actually be looking for in a video like this, the simplex method, as the most popular and most well understood method to solve linear programs. Rather than just stating an algorithm, the focus will be on actually understanding how the simplex method solves linear programs. We will also discuss other lesser known methods for solving linear programs, provide some more theoretical background, and introduce the very elegant and useful concept of duality in linear programming. So stay tuned, and thank you so much for watching.